that has a cap of 5. So if you don't register fast, then you have to play the game, because they don't want students just taking one classes, they want to distribute them. All right, before we get going, we will have the extra lectures on Friday, and I will discuss the course projects. So, and then the next 2 Mondays, we won't have lectures, and so we will be zeroed out. We're not missing any lectures. So it'll give you time to work on your projects. I'll be assigning like 1 or 2 homework problems. I think I've got them assigned out to the 12th. So I'll assign, like I said, 1 or 2, and the idea is there I don't want to burden you with, so you don't have too much. I want you to focus on your projects and learning, because I find that I have a fundamental thing. I think coursework is great, but I think you don't learn as much, or you don't learn in courses like you do learning doing stuff. So if I ask, okay, how did I learn things? I don't say, oh, I took this course and this course. That's not the way I learned. The way I learned was actually doing work and doing things, right? So here, like the coursework requirement for the PhD is like 10 courses. I think that's ridiculously large number, all right? I think it should be fewer, and you should be focusing on the research. But what do I know? Anyway, does anybody have any questions before we get going? And today we're going to cover pattern noise. We covered this a little bit already. Integrator, forward modulator gain, comparator gain, offset, noise, and hysteresis. No questions? Yep. Lay it on me. 930, yeah, the K delta 1 sigma one. Yeah. Well, that means you're not using the latest zip file, because the reason that you have that is if you use an ideal D flip-flop. Yeah, if you use ideal D flip-flops, that's why I had to go redraft that, and it took considerable time. So all those components you can use now, and you don't have to design from scratch. But if you try to mix ideal components and non-ideal components together, you're going to get things where they don't, because what happens is you get something that looks like this. Just so you know, I don't like magic, and so I want to make sure you understand what happens. What was today's lecture anyway? Lecture 19, and today's October 29th. So what happens is, in a real circuit, you get something that looks like this, right? As a clocking waveform. Well, if you feed that into a D flip-flop, that's ideal. And then you have an ideal clock. And if you're using, let's just say for the moment that you're using a clock generator that's a pulse source in SPICE. Just one sec. Then what happens is, in the real circuit, this is finite, so there's noise on the waveform. So when you start closing the switches at slightly different times, you can get it where one switch thinks that it's a 0 and the other thinks it's a 1, and so you get the 2 switches fighting and a huge current to flow, and then it locks it at half the power supply, or 2.5 volts, because it's finite step time. So this was, oh, okay, this is a 0, this is a 1, but because that finite change, it doesn't latch the right values. It basically does the following. If you look at the model, here, I'll show you. You look at the model, these 2 switches close, and you get the switch resistance like this, and so then it goes to 2.5. So if you look, here, I'll just show you the ideal, that model. You don't want to use that flip-flop. You want to use, I call it a D-flop. This one's the one I drew last weekend. It's with real transistors. And then if you use the ideal one, you see how it uses switches? And if you capture the value, like I said, where it doesn't capture the right value, it can come in and one of these switches, both these switches can be closed, and it pulls the output to 2.5. And so you get 0, step 2, 5. All right, any other questions? So key point, don't use ideal components. Life is much better with ideal components. You can do really good stuff because you make 0 loop delay and all these other things, but it's fake. It's not real. All right, any other questions on the projects or the homework or anything like that? So was there any questions on the quiz? Because that you should be able to derive, all right? How about the y is z to the minus 1? One thing, you know, when you put the comparator in for that derivation here, the output's only going to change every phi1, right? So it's, you can't, even if you do something here and you have this integrator, you know, when phi2 closes, this output of the op amp is going to change. But that doesn't have any influence on the output until after phi1. So it adds an extra half clock cycle delay to this part of the circuit. Now I want you to keep in mind that we did this already, because if you go back to chapter 2 and you do the same thing when you have phi1, phi2, I don't know if you can see that, but let's zoom in. You have phi1, phi2, and then phi1. Same thing. If phi2 closes, the output here changes, but if you go through the phi1 switch, it doesn't actually go to the final output until after the phi1 switch closes. Then you assume final settling on the falling edge of phi1 that you've waited the whole clock period. So it's the exact same thing. That's why if you go look in the table and you look at output connected to phi1, and you go, okay, v1, v2, or, you know, okay, v2 input, wait a sec. I was looking at this one, but v2 is this. And then it goes to, oh yeah, that's right. Vout's connected to, V2 is connected to Vout, so that gives you the extra clock cycle delay. So this would become z to the minus 1. Okay, if it's connected to phi1, adds a half clock cycle, and if you connected Vout through the phi2 switches, then you would just add a half clock cycle delay. So like this one here would be z to the minus 1 half. Would that even work? Because you would have a circular loop. You'd have something like that. I'd have to think about that. But one thing you can do is you can look at the simulations and see what things are doing. And you do that by putting in a DC signal and then looking at what happens on the output. You'll see this output changes, but then nothing happens until you clock phi1. For which, say this one? I'm not understanding. I mean, when you're taking the difference between the delta between the input and the fed back output. So if you look here in the more generic case, it'd be V in minus V out, right? And then you add that clock cycle delay so that this is delayed a half clock cycle and this one's delayed a whole clock cycle. So that's how you get the delta in the block diagram, V in minus V out. And then the sigma is the integration. No, I think all you do is you just put this is phi2 and this is phi1. Yeah. Yep. All right. Let's go talk about dead zones again briefly, and then all that other stuff. And this other stuff that we talk about, the integrator gain and offset, you're going to need to know that for the project. So it's important, okay? So we talked about for because you're going to need to know how to set your gain of your integrator and what's the maximum gain. But you know, we talked about this before. We said that, hey, if we get in certain situations, if there is a DC signal coming in where certain codes will repeat, and when those certain codes will repeat, we'll get a ripple in the output. We said that one way of getting rid of that ripple was to, does everybody remember that discussion, or do I need to refresh your memory? Remember I said that you have, and we did the continuous time case, I'll just do that again instead of drawing switched capacitors. And then you had this, and we said that when this signal's bouncing back and forth, that if we put a DC in here, then we can get a repeating tone. And if that repeating tone lies in the base spectrum, it can cause a spur or a impulse in the frequency response on the output. So a simple example of that would be, and if we put the common mode voltage in here, then we get 1 0 1 0 1 0, etc., assuming the loop is fast enough. If not, we'll get 1 1 0 0 1 1 0 0, etc. Does everybody remember that? And if I look at this tone, where's the fundamental of this tone? Well, first off, what's the distance between, what's the length of this 1? Wait a sec, what's the length of the 1? How often are we clocking that comparator? Yeah, every TS, right? Does everybody agree with that? So if TS is 10 nanoseconds, and I ask, what's the fundamental here that I would see in my spectrum? Yeah, it would be 2 TS or 50 megahertz, right? Does everybody understand that? Okay, if you don't understand, you understand? Okay, why don't you say, I don't understand, okay? So you understand that if I put in 1/2 volt here, okay, the output is going to be 1 0 1 0 1 0 because it's going to average to 1/2 volt, correct? Okay, so now if I ask if my clock period is 10 nanoseconds, the width of that pulse is 10 nanoseconds. Okay, so if I ask what's the frequency here, it's 20 nanoseconds. If I ask what's the frequency that corresponds to, it's 1 over 20 nanoseconds or 50 megahertz. And I believe I did this in chapter 2. For a square wave, you get first, third, fifth, seventh harmonics. So your first harmonic would be at 50 megahertz. So in this case, that's not that big of a deal. You're not going to see too much ripple when you filter because it's going to fall on a multiple of the clock frequency. Does everybody follow that? Okay, does that make sense now? All right, so what happens when I have like a 1 followed by like 7 zeros? Let's just put that in there. Okay, the frequency content is going to be something that has a higher frequency component and a lower frequency component. The longer the repeating stream, the more likely I'm going to have that repeating in the base spectrum. Here's where I have 1 0 1 0 for the output where it's bouncing back and forth. Now, of course, if I filter more, I reduce that. So what I want to do is I want to break up the tone. So what I could do, just make sure it's really simple. You ask, okay, well, how would you break up the tones? Here I say, okay, add a dither source. The dither source then modulates the VCM. Okay, so I want you to intuitively tell me, what does that mean? Instead of getting 1 0 1 0 1 0, you might get an output sequence that looks like this: 1 1 0 1 0 1 0 0. Oops, I need to zoom back out. And it makes it more random. Okay, so there's more noise on there. What's that? It averages over a long period to the exact same value, but you don't get the repeating tones. It's just like when they use frequency hopping, all right, where you're moving things. You don't have one frequency where you're getting all the energy. It's moving around, okay? So I get 1 1 0, and I look at this and I go, okay, here I have 4 1s and 4 zeros. If I average this, it still averages to 1/2. And so by doing that, I'm breaking this up. Now I just showed you a dither source. What was the more common way that we could do that by changing the topology? Yeah, use a second order modulator. The second order modulator, the tones in the output are much less of a problem because it randomizes things. So you get things not repeating sequences, but it averages out to the same value. Is everybody clear on that? Yeah, you have two feedback paths, both inputs are two, you randomize things, and so it's harder to get the repeating tones. So tones in higher order modulators, third, fourth, are just not an issue. They're really not an issue in second orders. They are an issue in first orders because you get, in the ideal case, things just repeating over and over again, okay? Okay, so I want to just make sure if somebody says, okay, that there's a repeating tone. Here it's not a repeating tone. Then we could go 1 0 1 0 and then 1 1 0 1 and repeat. But the average stays 1/2. If you have a repeating tone, what you get is you have your noise spectrum, but then you get spurs in the spectrum that are as a result of that pattern noise. And in digital signal processing, you probably covered this. It's called limit cycle oscillations. You didn't cover that? Okay. Well, limit cycle oscillations are very common in digital filters for certain inputs, and you want to avoid those because they do the exact same thing. They give you spurs in your output. Okay. So if we go second order, that's not an issue. If you do a second order K delta, it won't be an issue with a first order because you're going to have various paths and they're not going to fully settle. So you're going to have not repeating, so tones shouldn't be an issue. Okay, are there any questions about that? Stability. So remember that when we talked about the first order, it does this with shaping the noise. So this is the modulation noise, which is the noise transfer function times VQE. When you go to a second order modulator, it suppresses the noise in the lower frequencies, but then because it's a second order derivative at the higher frequencies, you get more noise, and it comes back down. And then in third, you get less noise in the bandwidth, but the noise goes up. So what they do in third and fourth and higher order modulators is they'll put some ripple in here so this goes up and then is limited so it doesn't keep going without bound. So if you try to use a simple third order differentiation, 1 minus z to the minus 1 in the noise transfer function, it becomes basically nearly impossible for single feedback loops to stabilize. We'll talk about in a week or so cascaded modulators where we use cascades of stable first and second order modulators to get higher order modulators. Okay. Are there any questions there? Okay, so what I want to do now, so key point here is that if you're using a simple first order, you can get repeating tones and you'll get spurs in your spectrum. So when you look at your output spectrum in the simulations, you'll see something sticking up, okay? What I want to talk about now is how high does the gain of the op-amp have to be for, or first I want to talk about and let's do a simulation for this actually. How high does the gain of the op-amp have to be, or how do I set the gain of the integrator so that I don't saturate the integrator? And I briefly talked about this last time without any math or any equations. I want to do it more quantitatively now. I want to start out with a simple example, and this is figure 243. And so let's go look at figure 712. And the gain of the delaying integrator here is CI over CF, which is just 1. And we talked about this last time. And this is the output of the integrator, the output of the op-amp. So when you do your projects, you have real transistor circuits, you're operating with a 5-volt supply. If you start to see them saturate when you probe this node, you have to adjust the gain of your integrator. Okay, so if you look at this, you say, okay, my power supply here is 1 volt and ground. You can see I'm using an ideal op-amp. It doesn't use a power supply. It's going beyond the rails of the integrator. Okay, so and how do I make sure that when this is designed, it swings within the range? And so if you go work at a company where they design data converters and they use delta sigmas, what they'll do, they'll say, we only use SPICE for checking things like integrator output swing, like this node right here, because it's such a digital signal processing intensive thing. They do a lot of the design using MATLAB, because everything's basically like DSP, okay? So you do the topology, the stability. If you do a real high order with a large number of samples, it's really not practical to do a SPICE simulation. You'll find out even with what you're doing that it's going to be a little painful waiting for the simulations. Okay, I'm hoping that because it's continuous time and not switch capacitor and you design everything with simpler components that it's going to be faster, but we'll find out, all right? But so they look at this, and then there's also limitations with the resolution in SPICE. It's tough to get beyond 10 bits without doing some things, and I actually put some comments here just if case. Where was the example of the continuous time K delta? Yeah, right here in the errata, right here, so you could see how to clock those switches. One example, where is it? So see SPICE simulation comments here. So if you look here, there's a bunch of things about SPICE simulations. When you're, and you need to understand these, when you're doing your SPICE simulation, if you pick sine waves, when you pick the length of the simulation so that it's different than an even number, or not an even, and a whole number of sine wave cycles, you're going to get weird signal to noise ratios, because you're going along and you're simulating and you get to the one point where, okay, I stop right here. Well, it's an abrupt stop. It's not stopping at a zero where you get an even number, because the way, and we'll talk about this later, the way the windowing works is if you can window the spectrums with a whole number of cycles in there, you end up not getting errors and reduce signal to noise ratio. So you'll need to look at this and understand. But in addition, what happens is SPICE has limitations on how the resolution. So if you have a 1 millivolt, which is common in SPICE, relative tolerance, that means your nodes are only getting to 1 millivolt. Well, if you're operating with a 1 volt supply and you want to get above 10 bits, well, you need to have simulations that resolve more than a millivolt, because that's 2 to the 10th into 1 volt is 1 millivolt. So you need to play games with the SPICE, which means you need to choke off you need to make the accuracy better, and then that increases the simulation time. Anyway, we'll talk about this more down the road. This is not just important for the projects, but it's also important when you're testing data converters to make sure that you do the testing properly so that you get good results, because you can screw up the test really easy. Okay. All right. So let's go talk about integrator gain. Everybody sees we want to reduce the gain, and you see, okay, well, how did we reduce the gain last time? Yeah, we made this one 0.4. Wait, it was wait, I'm sorry, we made one of these 0.4. We made this one 0.4, right? Because it's CI over CF. Whoops, let me see what I did in the book. Yeah, that's what I did in the book. And you see, okay, if we reduce it to 0.4, then we get bound to 90% of VDD and down to roughly 10% of VDD, and so that's reasonable. But what I want to do is I want to go through and derive that a little bit more. Before I do that, well, let's use this figure right here. Does everybody understand that idea? Okay, so you go through and you say, okay, this is CI over CF. You've derived that. That's from table in chapter 2, CI over CF. We get the extra half clock cycle delay as we talked about in the homework. This was the GC. So I want to go through and derive the transfer function. And you recall GC was, if I look at the, okay, so here's a good quiz question. Closed book, closed notes. Sketch the comparator transfer characteristic. Oh, okay, that's easy. Here's comparator. Let's just say we have the following. So we go to VCM, 1 volt, 0 volts, and then we go through and we say, okay, when Vin is less than VCM, the output is 0. Then it gets to VCM and the output switches to 1. and stays high. Okay, there's the transfer curves. How do I calculate GC? Yeah, I look and I say, okay, my output delta V out is always equal to 1. And then I look at how much my integrator is varying here, and then I do the change in V in, which is the output of the integrator, divided into the change in V out. And if my integrator's not changing very much, my gain is high. So GC is high. If my integrator's changing a lot, then my GC is low. Okay, so that's why I model this GC here in addition to the gain of the integrator. Does everybody follow that? Okay, and then I've asked this last time too. What's the problem with making the gain of the integrator really small? What is it? Well, GC grows if the gain of the integrator, GC has to grow, which means that the comparator needs to be better. It needs to be able to resolve smaller signals and perform better. Okay, we'll quantitatively discuss that later today, I think. Okay, so yeah, today in the presentation there was a comment, or there was in the dissertation, said, and the quantizer gain goes to 0. And immediately that set off a red flag in my mind, because what's the only way the quantizer gain can go to 0? What's that? Yeah, V out is 0, which means V out stuck, which means the input to the modulator goes to infinity, or goes to a large value, so that the output can never average, it can never get up, so it gets stuck, right? Well, I'm asking what's the benefit there? Well, it's always stable. Well, think about that. If the output's stuck, it's stable, but it's not worthwhile. It's not doing anything, right? To get quantizers gain 0, the input's above your range and the output's stuck at 0. So, or the output's stuck at a level and not changing. So quantizer gain going to 0 set off a red flag in my mind. So I had to ask that question. All right. So let's look at, I want to derive this. So let's do it real quick. And so let's call this x minus y. Yep. Yeah, you can't do, the problem is then if you're using a clocked comparator and you want to find the DC gain of the comparator, it's really tough and you need to move your input really slow, because if you do like the sim I put in there, there's a granularity in the clock size. So it could pass the threshold, but then you don't clock the comparator until 7 nanoseconds later, and then it looks like there's a big offset. So you follow me what I'm saying? If you go back to I forget which one it is, 922 maybe? Nope. Was it 25? Nope. 29? Yeah, this one. Okay, so in this case, VNP is held at 2.5 volts and VNM is just a little pulse here. Oh wait, this is the amplifier. Yeah, oops. Yeah, so here's the clock. So VNP is held at, VNM is held at 1.5 because notice, and again I'm going to go through the projects on Friday, this input is, since it's NMOS, if you drive the two inputs towards VDD, it makes them go into triode. So again, if you don't want to do any design, just use the blocks as they are. Don't mess with them. You'll need to change the feedback loops and the resistors, but if you've taken classes and you want to learn more, then once you get your design working, it would be really good if you tried to improve things by changing the designs, okay, but not necessary. Okay, so if you look at this node's going to switch, and so you look and you go, okay, cross the threshold right here, but holy cow, it's not switching until way over here. Well, there is a delay through the comparator, but also where you catch the clock edge, because there's 10 nanoseconds inherent delay here. So if I slow everything down, by a factor of 10, you're going to see this edge move way over here close to where the switching is. So let me do that. So let's just go and say, okay, I'm going to raise my V input clock pulse from 1 to 2. We'll do that. I can't change the clock, obviously. And then I'm going to change this. So I just made the simulation longer by a factor of 10, and then I increase the, oh, didn't I hit OK? Oh, 0 to 5,000. So I go look at it and I go, okay, where's it crossing the threshold? It's still going to cross it coming up here. Boom, there it is. Wait a sec, something's not right. So this one does have an offset. Yeah, it has an offset. Well, yeah, if you do it so it overdrives it, because there's obviously a teeny bit of memory still in there, but the offset's like 50 millivolts or so, and again, we'll talk about that. Okay. So let's go drive this real quick. And this would be GI, GC, which I think I called that GF, and then z to the minus 1 over 1 minus z to the minus 1 all over, or plus VQE equals V out, or equals Y. And so you notice that when we solve for the algebra, the z to the minus 1 is multiplied by GI, GC. So we can go down here and immediately write that y equals z to the minus 1 GI GC times x plus z to the minus 1 GI GC divided by times 1 minus z to the minus 1 times VQE. And then you go back and you say, okay, well, that makes sense. But if you look at the oh, wait a sec, that's not right. Oh yeah, that's where it comes out. This is the solution right here. I should have actually done the algebra. If you look at it with g of f equal to 1, which it will go to because of what we just discussed, then this reduces to what we had, z to the minus 1 times vn of z, and 1 minus z to the 1 times vqe of z. So a key point here is that the integrator and the comparator gains subtract out and give a constant, just as seen here in figure 7.28. That doesn't tell us how we select those, though, right? I mean, that just tells us that they subtract out. Okay, so well, okay, so how do we select it? How do we select that gain? Okay, well, let me ask this. What do I think about when what do I want? What do I want here for this integrator output to be? Yeah, as big as possible, but below VDD and above ground, right? I want it as big as possible because, as we'll see, it reduces the noise, but it minimizes the stress on the comparator. But I don't want it so big as the bucket's overfilling and the charge is spilling out. Does everybody follow that? Okay, so now we have to answer several more questions here. One is, I want to talk about the op-amp gain, but before we do, I want to talk about comparator gain, offset, and all that. We have to ask, well, okay, how big does the open loop gain of this op-amp have to be? Because if you look at the open loop gain of the circuit in chapter 9 that I put in there for the op-amp, it's not very high. And so why don't we pause and you tell me how to determine the open loop gain of that circuit. So let's go back to, so this, actually, let me finish the noise discussion, then we'll move on to the op-amp integrator discussion. The noise discussion is less than I mean, it's not super interesting, so noise and hysteresis and all that stuff. Comparator gain. Okay, so that path between the if I look at the comparator, I just showed I have an offset, right? So I want you to tell me qualitatively. I said, okay, here's my comparator, and there's the plus input, there's the minus input, here's my Vref, here's Vin, there's the clock signal. Okay. Tell me, how do I know this has an offset? So here's my Vref. Here's my Vin. Assuming the clock is fast relative to these two signals, where should my output change from a 0 to a 1? Right here, right? No offset. I just saw that I do have an offset in that comparator. So I go look and I go, okay, well, what actually happened was it switched like this. So I'm offset here. Instead of switching right here, I've got this offset, and so I've got this amount right here that I'm going to call VOS. So it's as if Vref were up here. So how do I model that in my circuit? Yeah, so I add the offset like this, correct? So I go, oh, so I get, let me make sure, offset can be positive or negative unless it's something that's designed into the circuit. So let's write it like this. And so I model it as an offset right here. Does everybody agree with that? Okay, so then I ask, okay, well, how does that influence the behavior of my modulator? And let me also point out that when I do noise, I model it the exact same way. So if this is noise or offset, or if there's a little bit of a hysteresis, instead of it always switching right here, when I go the other way, it switches right here, and I have a little bit of a hysteresis, I model it as an imperfection on the input of the op amp. Does everybody, or comparator, does everybody follow that? And why? Now it's not going to be, if there's hysteresis, it's going to be a different value going up versus going down. If there's noise, it's going to be randomized. That noise will then influence where the output of the comparator actually switches, but it's all modeled right here with the source. Any questions? So now let me go draw a simple block diagram. Here I'm going to draw my integrator. I'm going to draw it just, instead of as a switch capacitor, I'll do it in the continuous time domain as 1 over S. Then I'm going to go draw my comparator, but I'm going to put my noise, just talk about the noise here, the offset, and I'll draw it as a random source. And then here's my comparator. Where's my input signal come in? Yeah, right here, right? I'm not drawing the resistor and all that. I'm just writing the op amp as an integrator to get the point across. Okay, so I want to see how this comparator's offset is influencing the input. So my comparator's offset noise, I'm going to refer it back here, because remember, this is a model to predict what happens here when I don't switch at the right place. So I refer it back to the input. So what I want is, I want a source here that is the equivalent once I refer it back here. So I'm going to go put this as VOS. And I'm going to go to 1, or we'll call it VOS prime. Then I go 1 over S again, and then my comparator, and I get the same output. So I got, okay, well, how do I get this value times what this is? So I know this value, VOS prime, times 1 over S, would then be equal to VOS. Yeah, so what I'm doing is I'm dividing by the gain of the op amp. I'm essentially saying that VOS prime is equal to VOS divided by 1 over S. Does everybody follow that? So at DC, what is S? 0. So how much of that noise at low frequencies propagates? Nothing. Then as I go higher and higher in frequency, the gain of this drops, and this refers more and more directly to the input. The key point is, because I've got this really high gain stage, and keep in mind, it will be high gain because when I'm doing oversampling, that's one of my requirements, is that this is high gain in the signal bandwidths of interest. This noise from the comparator will be pretty much irrelevant. If I make a mistake, it's pretty much irrelevant. If I have offset, it's pretty much irrelevant. So if I had 50 millivolts offset and I had a gain of 1,000 here, then I've got 50 microvolts input referred offset over here. And you're saying, well, of course, that's nothing more than you repeating yourself, because you already told us if we make a mistake with the comparator, it averages out. Okay, there's nothing new there. But here we're showing mathematically why that's the case. Okay, so I got a question. Does anybody have any questions on that before I ask my question? Okay, what if I have offset noise, offset or noise? I won't have hysteresis because that's not a digital circuit. Here with this integrator, what happens to it in the input signal? The input referred offset of the op amp, because the op amp's not going to perfectly be switching it plus and minus right there. What happens if I have offset noise here with the op amp? It's not going to refer back by dividing by some high gain, right? So it's going to add directly to my input signal. So if I have an offset in my op amp, it's going to shift the output signal by the offset, because it adds directly to the input. I don't believe you. Prove it. Okay, I'll prove it. Let's go look at figure 7.14 again. And let's put some ridiculous offsets in there. Let's do it for the comparator first. Let's go, well, let's show what it looks like. Output, input, and you know what? Let's throw a filter on there so I can see some filtering, because I don't like looking at ones and zeros. I like looking at analog waveforms. So what was the input frequency? It's 500 kilohertz. So let's set this at 500. And 500 kilohertz would be 2 microseconds period. So if we put this at 1,000 puff, would be 1 nano. I think 1,000 puff. And then let's go get the old hand out here. Get the scissors out. Rerun the sim. Let's just see what happens if we use 100. That'll probably be too ripply, right? Good enough. Everybody would agree? Because I just want to see what happens if there's an effect on the output waveform. So what I'm going to do now is I'm going to go get the hand out here, pull this up, and then I'm going to copy this DC source, plop it in here, and I'm going to put a ridiculously high offset of 100 millivolts. So instead of there being 500 millivolts here, now there's only 400. Now I'm going to rerun the sim. Looks exactly the same. Of course it does. To refer that offset back to the input, I divide by the gain of the op amp. Any questions? So it doesn't have any influence. It's just like me picking a different water level in the bucket. Okay, so now I'm going to go do the same thing here. Let me get my hand out here. Move this dude back. I'm going to stretch this one over. Yeah, let's just put it here. Plop this in here. And I'm claiming this will add directly to the input signal. So what I'm claiming is that I'm going to see the blue shift 100 millivolts because there's no attenuation, there's no dividing by the input source. Would everybody agree it shifted? Then if I flip it around, Control R, and I rerun the sim, it's flipped the other way and it saturates. Any questions? Yeah, you want to have high open loop gain and you want to have low offset. So let's do one other thing before we move on. How do I determine, which I was going to do before we talk about this discussion, how do I determine the gain of that op amp, that amplifier that's used in chapter 9? Okay, if you've done analog, you can do it all kinds of different ways, but let's show you a real simple way. So I'm going to just go into that. I think it was 922, was it? Nope, shoot. Past performance. Yeah, this one, right? So what I'm going to do is I'm going to change the tran. So let's just run the sim first. And I look. Now, the reason I picked that op amp is the outputs are a VGS, and those go into the comparator, so they fit well together. So comparator inputs are two NMOS devices. This amplifier's outputs common mode signals, the VGS, so they go and meet together and meet well, all right? It's not like these swing around VDD over 2 and the comparator inputs swing around VDD over 4. They're both going, gate drain connect or gate source voltage out to the next gate source voltage. So I'm not going to drive anything real deep into triode and kill the gain, all right? So what I want to do though is I want to determine the DC gain here. And the other point is it's fast. When you're doing your designs, you need an amplifier that has fast settling time, or else you're not going to ever be able to keep up. It's like you dumping the water in, but it takes you so long that the decisions that the people that are following you make are just irrelevant nonsense. You need fast settling time, okay? So I'll go back here, and I'm going to, looks like I already did this. I'm going to put it, oops. I'm going to put a DC sweep, and I'm going to sweep the input from 2.4 to 4, 2.6 rather, and I'm going to look at the output. So I look and I say, okay, my input goes from 2.4 to 2.6, and my output goes from 0.6 to 3.6. So this is how much my output's changing. So if I look at, like, say, right around here, the input wiggling back and forth. What kind of wiggle do I get out? That's the gain. How do I plot that? Yeah, I take the derivative of the output. Oops. The output is only, let's get rid of this trace so that you don't, the output's only like 22. And you go, wait a sec, can you really design a data converter with an op amp that has a gain of 22? Apparently you can. Okay, so just out of curiosity, if I wanted to increase the gain of this, what would I do? Let's go back and increase the gain of this topology. Well, start when you're really high speed, you don't want to have hot cascades. Yeah, I got to decrease the current. So if you decrease the current, say I go to 10, and I redo the sim, my gain shoots up a little because I've reduced the current. However, let's see what happens to the pulse response, if you can remember. Yeah, it's going to be slower because the gain bandwidth product's constant. So you can see it's a little slower. And just so you can see, let's go back and change this back to 30. Hit run. So mental picture, roll them. You can see a little bit faster response, especially noticeable right here. Okay. You can try it. The problem is that stability, if you cascade 2 diff amps, remember that's like a 2-stage op amp, and so you need to start playing some games because it's impossible the way the poles work out to not get 180-degree phase shift and instability. So if you're going to use 2 cascades of these guys, then you got to feed from the output back using pole splitting, a capacitor, and compensate it. So I'm not saying you can't do it. I'm just saying it's not going to be, you're going to chase your tail if you just put 2 diff amps together and think that's going to work. Okay? Because it's classic problem. You understand why, right? Yeah, because you have the 2 poles you can't get rid of. They're at the same frequency. You will have 180-degree phase shift in the feedback. Yeah. Well, it'd be nicer if it wasn't. You can design a better one. I picked this because it's easy and, you know. But let's go talk about, now we said the gain here is 22, so that sets the stage for the next discussion, which is how high does the integrator have to be? And the point there is that, and actually let me show you what the simulation, whoops, what did I change here? Whatever. Save changes. Sure. Let's go back to that plot we just looked at for a moment ago, and I want to show you something before we talk about this next discussion, which is if you look at, just look at, there's the output. I want to focus more on V common mode. It's at 500 millivolts, and then this voltage here, which is also at 500 millivolts, and you see a little bit of a difference, right? Okay, so now what I want to do is I want to go down in, and remember, in an op amp, you might have learned this in circuits, you always say, oh, this terminal is equal to this one. Well, in real life, that's not the case, because the op amp has finite gain, and only when the op amp's gain is infinite do these 2 terminals become the same value. So I want to go in now, and I want to change the op amp's gain here to 22, which is what we had. So the current V plus minus V minus times 1 ohm times 22 gives an open loop gain of 22. Does everybody follow that? Okay, so I'll go back now. Keep in mind what I have here is VCM and the inverting input of the op amp. So now watch what happens. See how that inverting input of the op amp's wiggling around? That's what you see with common mode gain. And so if I look at what the output does, the output is going, am I losing anybody here? Okay, so the output is going to do the following. Before we show you, let's write it. The output is going to look like this. V out, whatever, what did I use in the book? NTS is going to be equal to A open loop, which is a function of frequency. I'll just write it like this, times the voltage on the positive input, which is V in of NTS minus VCM. Okay, so does everybody agree with that? And let's prove it. Okay, of course, Vn is reference to VCM, so in the remainder of the discussion, I'm going to assume Vn is reference to ground, so I don't have to write all of the VCMs. But does everybody agree with this? It's the open loop gain times the voltage on the positive terminal minus the voltage on the minus terminal is equal to V out. Okay, so it's just AOL is equal to V plus minus V minus, and AOL goes to infinity, V plus has to equal V minus. Okay, same old ideal op amp. AOL goes to infinity, V plus equals V minus to keep the output bounded. Okay, so I go back here and I go, heck, I got the voltage on the inverting input here. Let's go add a plot plane. I know what my gain is, so let me go actually, let's plot V out. Where is V? V out integrator. There's my V out integrator. Let's go say, hey, this is minus 0.5, and then it's times 22, and see what I get. So does everybody understand this? What I just wrote is this right here. Well, if I'm off, it'll just be the negative. Okay, so I hit OK, and it is the negative, isn't it? So let me flip them around. Uh, 0.5 minus. And then I say, okay, let's get rid of the startup transient. Why didn't it? Why is... That's too easy, man. 0.2u. Okay, so then let's pull this up here. Hey, they match! Of course they do! Alright, any questions? Okay, so now what I'm going to do... Sure. I'm going to go back over here, and I'm going to not write this in terms of VCM, and then I'll write that what did I call this? V minus. What's in the book? In the book, I'll just V minus is equal to V out divided by AOL of F. Anybody disagree with that after I just said let LT Spice prove that what I did was right? So now, when I look and I use this equation, what I can write now for, I'm going to go back and you can look in the book in figure 730. What I'll do is I'll write, when you derive those discrete analog integrator, what you get is you get the following. Again, you don't need to put the VCM in there. I did it in the book, so... So this one, a little bit sloppy. This one is not with reference to VCM. And then what is this right here? This one is with reference to VCM. So you really don't need to carry it through, but just to be consistent with the book. And if you follow through the derivation, let me ask a simple question just to make sure everybody's following. If I have an ideal op amp, which was what was used in chapter 2, what is AOL? Say, and this reduces to what we used in chapter 2 to do the derivation. So when I go through and I write my output, what I get is I get my integrator gains being modified. And actually, I don't want to write all that out, so I'm just going to be lazy and show you. Get the following. And so you see that the integrator gain is influenced. And so you'll get, instead of the integrator gain going to infinity at DC, it goes to a finite value. Just out of curiosity, what's the finite value that the integrator gain goes to? Just think about it. Don't look at the equations. What's the maximum gain that I can get through that integrator? I ask easy questions, always. No? If I look at the op amp, here's my op amp, has a gain of 22. What's the maximum gain I can get from here to here? 22. When I don't have any feedback, the capacitor is an open, I put a signal here on the input of the integrator, the output of the integrator is going to be 22 times larger. That's my open loop gain. Is anybody getting confused on that? 'Cause super simple. So what this is showing is that at DC, instead of me going to a gain of infinity, I'm going to go to a gain of AOL. So then I can go and ask, all right, well, if I look at this compared to the ideal, when the ideal, this term is 0, and this term is 0, and this term is 0, I can write that I've got a gain error term, which is given by this. So if you go back and you say, okay, well, that makes sense because the error is proportional to CI over CF, which I said I want as big as possible because then it puts less stress on the comparator and I get less input referred noise. But here, if I make CI over CF big, I get more gain error. Okay, error due to gain. And so I want this to be as small as possible, and I want an ideal comparator. Okay, so in I think this is, let me just double check how I did today on finishing. Oh, I'm actually a little ahead. Good. So integrator, op amp. So I'm getting through this, so I'll move this down. But I do want to finish this. I tried to be more conservative when I set the schedule this time. So if I look, the noise transfer function, okay, so wait a sec. How did I get this equation? It's just this term right here. 1 plus the gain error minus z to the minus 1. 1 plus the gain error times z to the minus 1. What I'm going to do is I'm going to put in the value for z so I can get a frequency domain response. And then I'm going to repeat and calculate what the quantization noise is with that gain error. And of course, if the gain error is 0 with infinite open loop gain, then we reduce to the ideal situation here. I'm sorry, here is. And so what I said here is, okay, if we assume this term is small, 0.01 is squared is 0.0001, then this term dominates, and in a practical case it is. And you ask, okay, well, if I look at this, how big does the open loop gain have to be? Remembering that CI over CF times 1 over AOL. And if you look at that, if you put it in here for the this term right here, I'm skipping too much. Let me back up and write it. If you look at that second squared term, what you get is this is the second last part of 7.36 times Fs over 2K, and you assume that this is small, and it's small compared to is small. We'll just leave it at that. If I plug in the gain term, I get 1 over AOL times CI over CF. I don't want to carry that through. Squared times Fs over 2K. If I look at the DC component, and we'll talk about op-amp settling time in a moment, then AOL, this term right here, in order for this to be small, has to be greater than K. And I'm still leaving stuff out, so let me point this out. So if AOL is equal to K, this becomes K squared, right? And if I go look at the remainder of the equation, there I get a K cubed term. And so if I plug the numbers in, the values here, then what I end up getting is that this term becomes negligible if this is significant. So let me ask some simple questions here to make sure everybody's not lost. Why aren't I focusing on this one? Why do I not, in this text, why am I not bringing this part up? Okay, so what's a typical value for AOL? We just used 22. So what's 1 over 22 roughly? 0.05. So then we have a gain of an op amp and say it's 0.4. Okay, so if we have gains that are 100 or 20s or whatever, then 1 is much larger than that gain. So that's not a big deal. So I'm not focusing on this part. I'm focusing on this term right here, as this term being, okay, well, where does the gain start to be significant? And you could also, if you wanted an even simpler equation, you could say, okay, well, I want E gain to be much, much less than 1. So what if we did that? What would the result be? What's that? No. Let's say I focused on this and I said I want E gain to be less than, much, much less than 1. Or let's just say less than 1 so that it's not an issue. So I say, okay, I want E gain for that part to be less than 1. I say, oh, that means that I want 1 over AOL Ci over Cf. Then we'll just say that's 1 for the sake of argument to be less than 1. And it says I want AOL to be greater than 1. Or if I put the less, so that's not that interesting, right? Would everybody agree with that? Okay, so then if I go over here and I look, okay, well, if I look at the second term here, I say, well, okay, where does the gain error come into play? I want this term to basically be 0. Okay, if this term's basically 0, I can do that, then I can neglect this. So if this term was 0, okay, then I say AOL is equal to K. So then this becomes some constant, we'll say proportional to 1 over K cubed. Does everybody agree with that? And if it becomes K cubed, and I go compare that to what I have here, and I could put the FS and the 2 in there if I wanted, I compare it to what I want, then this term becomes negligible to this one. Okay, why is that important? If this term's negligible to this one, then I have the ideal case, which is represented just by this first part, and so the op-amp gain becomes unimportant. Did anybody follow that? Okay. All right, so does that make sense? The key point is, if this term becomes small, then I can just say, okay, well, I want AOL to be greater than K. So now here's where you say, okay, well, does the data converter fail if it's less than K? No, it just doesn't give you as high a signal-to-noise ratio, which is a big deal for manufacturability. You ask now, okay, well, how does it degrade the signal-to-noise ratio? You can go through the exact same derivation, and you can put in the you can add the gain term here. Of course, if E gain is 0, then this term goes away. At the same time, you can look at the op-amp unity gain frequency following similar arguments, and you want it to be unity gain frequency to be at least F sub S over 2. And the key point here is that, okay, well, I don't need a good op-amp. I can have an op-amp with a low gain, and I can have an op-amp that has a bandwidth of F sub S over 2, and the data converter is still going to work. Does everybody follow that? Okay, so I'm going to talk real quick about bandwidth, and then we'll quit. Are there any questions? All right, real quick here, because this is something maybe you already know. But if I look at the bandwidth of an op-amp, if I look at an op-amp's bandwidth, or I look at the gain bandwidth product of an op-amp and I plot with frequency AOL of F, I get something that looks like this. This is the unity gain frequency, this is the DC gain, and then this curve is AOL of F is equal to AOL DC divided by 1 plus JF over F unity times AOL DC. And so what I'm saying now is that when I go back and if I have a gain of 10 op amp, the simple way, without looking at any math, is you say, okay, gain of 10 is 20 dB. I get curves that look like this. And so they are limited by the op amp. And so I'm not going to go through the op amp theory. It's in chapter 3 if you want to read it. And I doubt very seriously we'll get to chapter 3 because there's still a lot to cover, but we'll see. It says the end result is your bandwidth only has to be F sub S over 2 for the op amp to work. Okay? Any questions? Did we cover enough today? No? It's like, is he serious? All right. Have a good day. Hopefully we'll see you on Friday.